Okay, okay. The quiz material ends right now, and we begin talking about something completely different. It's not on the quiz tomorrow. Okay. All right, let's talk about average value today. Your goal will be to find the average value of a function, and there is a huge twist at the end.
It's 0.
Right. We're about to generalize, friends. Are you ready? The notion of an average. Okay, so what is the average of these 5 temperatures? Or rather, I don't actually care. How would you compute it? Very good, class. You would, let's make something that is elementary school math look really complicated though. Does that look good? Right? No, I'm just saying it is very easy, but doesn't it make it look really hard when I write it with a sum? Okay, all right, good. That is in fact how you compute an average. What about the average temperature over 24 hours if it's governed by the function f of x, and f of x is some smooth curve? Valid question, first of all. Don't you agree? The temperature changes in a continuous manner throughout the day. How do we calculate the average temperature throughout the day? Suddenly, we're a little bit stymied, right? Easy elementary school question. Perhaps a question for calculus students down here. Even though it's the kind of thing that you might like to know like every day. Even what's the average temperature? It's the average of a continuous function at all different kinds of times that it moves smoothly throughout the day. What would be a first thing you might do if you're still just an elementary school student though and you didn't know anything about calculus or anything?
Get the points and then do it all.
Yeah, just like get a bunch of points and average them, right? Like that's in fact probably what even the weather person does, yeah.
I would say you do it on like one side because there's a duplicate of everything except for the one on top.
Okay, yeah, well this one happens to be symmetric, so maybe you just, okay, I'm with you. All right, but yeah, maybe we calculate a bunch of times, the temperatures at a bunch of times, and average them. So that's what we'll do here. Yeah, go ahead.
I was going to say gas. I agree. Look at the
Just kind of eyeball it. Right about there. All right, so let's suppose, as usual, we have, let's say, n rectangles, and so delta x we're taking to be b minus a over n. And so one way we could say this, too, is that if we know what we want delta x to be, we could think of, if it's 24 here, 24 hours, it'd be 24 over delta x. You rearrange that expression. So the average temperature is, of course, the same thing that we set up here, except instead of Ti, I've got f of xi. So this is us evaluating at each of these heights, and then dividing by n. So we're adding all those up. N is, where am I getting this? Oh, from down here, right? N is also known as 24 over delta x. I just flipped it there. But we have delta x over 24 times all these functions, the sum of all these function values. Or, of course, 1 over 24 times this sum, where delta x is a narrow amount, whatever you like, right? You could make it, I don't know, it looks like, what does it look like there? I don't even know how many there are. Does it look like there are 16 rectangles or something? I don't know. So each one is whatever 24 divided by 16 is in width. So the reason I like expressing it this way is because now I have this sum from 1 to n, and I can take the limit as that goes to infinity. And what is the limit of this expression as n goes to infinity? This guy right here, the limit of this sum from 1 to n of f of xi delta x. It's almost exactly the notation we have used already. For what? Right now it's an approximation. Approximate. Yeah, when we take the limit, this thing here becomes the integral. This thing becomes the integral from 0 to 24 of that function. So in the limit, we're adding up all of the temperatures. And we could have maybe started just by saying that. You might have been like, well, let's just add up all the temperatures and divide by 24. The length of the interval. Adding up all the temperatures is a little weird though with a continuous function, right? But we know how to do that. We got the integral. So there it is. The average temperature will be 1 over 24 times the integral, the area under the curve. So another way of saying it, well, let's make sure the units work out too here. What will the integral come out to be? If this is, say, hours, and this is degrees Fahrenheit, it'll be in like hour degrees, or degree hours, right? But then what is the 24 out front measured in? That's in hours. So it's 1 over 24 hours times something that's measured in degree hours. So in the end, you get an answer which you probably would have expected the units to be in just degrees. So yeah, this comes out to be in degrees, which makes sense because we're calculating average temperature for the day. Just want to make sure this all works the way we thought it would work. So can you give me a general rule yet, especially staring at what we just have here? If this calculates the average value of this temperature function f over 24 hours, what do you think one does in general to calculate the average value of a function over a given interval from, I don't know, A to B or something? Evan, go ahead.
Take the integral divided by the interval?
Yeah, integral divided by interval, right? So we'll put that in a box in a minute here, but I think you can already see where this is going. Let's talk about velocity. We love to talk about average velocity too. What's the average velocity of this particle? Here's a VT graph. Its velocity is 10, whatever, meters per second over 2 seconds. What's its average velocity?
10.
Very good. It was in fact not just averaging 10 meters per second, it was actually going 10 meters per second at every moment during those 2 seconds. Let me give you a slightly harder one. What about this one?
10.
10.
Why is it 10?
1/2 base times
Because that's like the half.
Yeah, because it looks that way. Yeah.
Half the area.
Well, yeah, there are kind of two ways to conceptualize it. One is to be like, well, this looks like kind of the average. The other is to think, well, this is 1/2 based on height. I went 20 meters. How do I know that? You can't really see it maybe, but that's 20 meters. This is 2, so 20 times 10. What's the distance you traveled during that time? The answer is 20 meters. And you did it in 2 seconds, right?
Those are wrong units. It's 20 meters per second over 2 seconds, according to your graph. Your velocity can't be 20.
No. The integral, the distance you covered is 20 meters. So this is 20 meters per second high.
Yeah.
This is 2 seconds wide.
Yeah.
Multiply them and divide by 2. Tell me what you get.
10 meters.
Good. No. You didn't.
20 meters over 2 seconds.
No, it's 20 times 2 is 40 divided by 2. So it's 20 meters. This object went 20 meters. Just like you did here. You went 20 meters over here, didn't you? 10 meters per second for 2 seconds. All right, so in both pictures, you end up 20 meters from where you started. And in both pictures, it took you 2 seconds. So in both pictures, your average velocity was 10 meters per second. Because we're disregarding how you got there. Here you had a nice 10 meters per second steady pace. Here you were ramping up your velocity, but in both cases, you hit the 20 meter mark at the same time, 2 seconds. So your average velocity in both cases is 20 meters per second, or it's 10 meters per second. The other way someone said to conceptualize this is just to think like, oh yeah, you could kind of like see that that's the average, maybe just by drawing a line there. What about this one? If I tell you that this area is 20 meters, then what's the average velocity? Of course, it's still 10, really 10 meters per second. Of course, we don't really care, and you can maybe even conceptualize it the same way we did up here, right? You said, this goes back to who said, let's just kind of eyeball it with the temperature, right? Was that you, Jack? Right? That's kind of what I'm appealing to right now to some extent. I'm thinking, yeah, you could almost eyeball it. You could be like, it's about 10. This piece could like swing down into there, you know. You could fill it in, it'd be 10, you know. Same thing here. So by eyeballing it, really we mean, let's be more particular about what we mean by eyeballing it. We mean, what rectangle could you squish the function down into and have it be a rectangle, right? So, yeah, if the answer is a rectangle of height 10, right, your average value is 10. But of course, they're smushed into a rectangle. But again, the point on these 3 pictures is the integral divided by the length of the interval, which is what Evan already said, right? Calculate for average velocity, calculate the distance you traveled, and divide by the time it took you, regardless of what crazy method you took to get there. All right, so let's finally put that in a box here. So it's not in a box. That's sad. Okay, whatever. I promised a box. Integral divided by interval informally. But the integral from a to b of f of x dx divided by b minus a, wonderful. So let's go ahead and find the average value of this function on this interval. This is a parabola on this interval. And what will you need maybe in your life? If you have a calculator. I'm just saying, right now you still don't know how to come up with the value of the integral of this without your calculator. So let's use f in it to help you out with this, okay? So write out what you're going to do, but then feel free to just ask your calculator what the answer is. Once you have, once you have some evidence of the work. We're good. So, what are we writing down here? We're writing 1/3 times the integral from 0 to 3. What do you get for the integral? 4.5? So this doesn't come out super nice. It's, what was that, 9/2, so 1.5. Oh, that is nice. Is that believable, by the way? I don't know if you looked at the graph. 1/2 x squared, 1.5. Seems like maybe it's the average value. Okay. There. I think it does look reasonable. Yeah, does that look straight? See my picture? Yeah, it looks like this piece, believably, has that much area. Looks good. This doesn't really come up very much in this course, but it's worth mentioning right now. I just promised that, I've never seen this particular form used on like AP tests or anything like that. But it's like, if you're ever going to say this, this is the time to say it. And after the last picture, it kind of makes you think that this should be intuitively true. In fact, you could try to draw a function, convince yourself that this is true, but drawing a function and seeing if you can draw a function that doesn't achieve its average value. Of course it achieves its average value, right? You could you can have it be constant and then always at every moment achieving its average value. But if you make even one part of it higher than the average, you know that another part will be lower, and if it's continuous, then it will achieve its average value, right? So this is sometimes called the mean value theorem for definite integrals. So I don't need you to know anything really, I don't know, about this really at all. I don't know that anyone will ever ask you anything about this. It just, if you're ever going to know it, now's the time to talk about it, right? It's pretty clear that this function needs to cross this horizontal line at some point, that's all. It's worth mentioning, but we'll move on. So for some C, notice that it feels very similar to the mean value theorem of old, right? For some C, in the interval a to b, we're guaranteed that the function achieves the average value. And later, we might even be able to say something about the fact that they're equivalent, the mean values are in this theorem. Yeah.
So it's like you want to have the same number of points above as below?
Well, not so much that. It could be that, I don't know what you mean by points. There are an infinite number of points
Like,
on the curve.
like in space?
Yeah, I mean, there'll be, you're actually making a stronger claim. You're saying that the area above this line and below will be equal, right? The area difference or something. Like this sliver will be equal to this sliver or something. Yeah, it's actually making a lighter claim than that, a weaker claim than that. But yeah, you're right. It's just saying that this function, no matter how you draw it, will cross the horizontal line that represents its average value at some point, right? It'll, at some value c, the function will equal its average value, right? Again, if you like make this function above the line here, then you know it's got to be below the line somewhere else to actually have that be its average value. So it'll cross the average value. All right. Let's practice some more here. We've got this time a velocity function. We're doing a little more real world feel. So go ahead and try this one here, and then we'll turn our attention to the one on the bottom in a second. The particle moves forward and backward in a line with this velocity. Find its average velocity over the first 3 seconds. So go ahead and, again, feel free to use your calculator to help you. And we'll report back in a second.
Hey, are you guys doing work? Alex, what'd you get for the last, like,
Jackson, are you paying attention?
I am. Thank you very much.
Why are you wearing a hoodie?
Hey, get off your phone.
Robert.
Integral over integral. Integral is 0 to 3.
So yeah, well, it feels similar to other ones we've done. What is it, 1/3? From 0 to 3. What's the integral come out to? 7.8. 23.625. Can someone confirm?
Yes.
And then that comes out to, what'd you say,
7.875.
7.875. Confirm?
Good job, Derek.
Thanks, Jack.
And what are the units? Of course,
Meters per second.
still meters per second, because of the way we talked about how this is going to come out. It'll come out in meters per second. Even though the integral itself is in meters, this will come out in meters per second. Okay, let's try this one down here now. First, before we do this one, I want you to notice how this problem is different. Some of you are like, just jump right to the formula. I think I've got this now. I just plug this in and I'll just do. Careful. Why is this problem different? Yeah, notice that the difference between these problems is that this says position.
We need to take a derivative.
So one way to do this would be to take the derivative so that we have a velocity function. Wait, but maybe you don't have to do that. Let's back up. Let's all get some perspective. Listen,
Oh
guys.
my gosh.
Wait, hold up. No.
Wait, can we back up?
Yeah, we can go back up here. Just F in it. Use your calculator to get this. Use your calculator to integrate this from 0 to 3.
Get the velocity, you take
All right,
the derivative
so-
of the position, right? And then you have to take the integral velocity.
Wait, I wanna back up a notch here. Go way back out. Way back out. Can we rewind back to Unit 2? Unit 3, I guess, when we first learned about rates of change. And that was the first time actually that we ever talked in this course about the average velocity. How did we compute the average velocity back then? We didn't know anything about integrals then, so how did we do it?
So mean
No.
What is that?
How did you do it back then? I would have given you this problem verbatim in back in Unit 3. How would you do it back then? Yeah, you do the slope of the secant, or how are you going to say it here?
Well, I was gonna say like you do the average of like the first and last point. Something.
It's not really the average of the first and last point, but yeah, you take the first and last point and find the secant, right? Right? You're just coming back? So what you were saying is you do x of 3, you calculate where you end up at 3, and you calculate where you are at 1, or 0, sorry. And then what? Divided by 3? Okay. So I just want to remind you of things you once knew. So what does that come out to be? What do you mean? Has anyone run this yet? So go ahead and do this. You plug in 3, plug in 0. And then someone else has already said one way to do this, like another way to do this, your first instinct actually today was to take the derivative and do it the way we've been doing it today. And my question is, are those the same thing? That is, like if you integrate from 0 to 3, the velocity function, is that the same thing? Hopefully they give the same answer, right? What do you get here? Well, I'm just saying, we talked about 2 ways now to talk about the average value. One way is back in unit 3 or whenever that was, right? Just find the difference in the positions and divide by the time interval. 3 minus 0, right? And the way we did it today is we said calculate the integral of the velocity function, not the position function, and divide by the size of the interval. And we said both of those are good ways to calculate the average value. So let's just, the average value, the average velocity, right? So what does this come out to be? Okay, 7.875. And the units, are the units meters per second here too? Yeah, because this is meters, this is seconds. What about over here? Do you get, well, I'll just say they're equal, right? 7.875 meters per second. Yeah, what did someone notice already about these 2 problems? What do we say? Yeah, when you take the derivative of this, I just set this up so that it would be this, right? So I want to make sure you understand that the approach we have here and the approach we have here is the same, which really, like I said, kind of makes your head collapse a little bit. You're like, wait, does that mean that these 2 things are equal? Not just for this function, but maybe in general for any velocity function and any position function? You see what this is saying? I mean, the 1 over b minus a is almost, I don't care. You know, it's like the fact that this integral is equal to this is very interesting. More on that later. Okay. I should give you your homework. Oh my God.
Because it's position per time. I know. It's almost like
I told you there'd be a twist at the end. You figured it out?
yeah, that's why I called it anti-theorem.
I see.
I'll come back.
I didn't realize that we had an I thought I was
She knows exactly why.
Sorry, the lesson ended a little early. Is there anything we want to do for 5 minutes?